So we have the pleasure today to receive three MPP colleagues, Emily Adlam, Kelvin, McQueen, and Kai Waegell. As you pronounce, Waegell?
Waegell. Waegell.
Waegell?
It's not the original pronunciation. That's how my family says it.
Okay, what is the original pronunciation?
Say it again?
What is the original?
Alsatian. Alsace-Lorraine, France?
Yes.
Oh, yeah, it's a unique name only from that region. Yeah.
Okay. Okay, and the talk will be on agency cannot be a purely quantum phenomenon. So I think that our colleague will argue why it cannot be. And so I leave them to present. Of course, the format is the usual one, presentation, they present, but if there are questions about comprehension, understanding, of course, you can interrupt. And by then, there will be final discussion. And then at least there will be a dinner provision, and possibly also dinner. We will see how many people want to go to the dinner. Okay, please.
Okay, thanks for coming, everyone. Thanks, Marco and the MPP program for hosting Emily, Kai, and myself. We're happy to be here. So this is part of the John Templeton funded project that several of us are involved in, especially Andrew Jordan and Matt Leifer. So this project is composed of 3 sub-projects. And the overall goal of the Templeton project is to make Chapman and especially the Institute for Quantum Studies a kind of hub for interdisciplinary quantum foundations research. And it's split into 3 sub-projects, and sub-project 3 is called Quantum Agency. And so this paper is a component of that sub-project. Okay, so what I'm going to do, I'm going to just start by clarifying the question that we're trying to answer today, and then I'll tell you how we're going to go about answering it collectively. So the question is a purely quantum agent possible? So we're talking about what we're calling purely quantum systems and asking whether such things could be agents. So a purely quantum system is a physical system that evolves unitarily in accordance with the usual rules of quantum mechanics in a coherent regime without decoherence or collapse. So removing decoherence and collapse from the equation basically means we're removing possibility to get classical phenomena, classical emergence, because we're really trying to focus in on a very quantum system. Okay, we'll say a lot more about that notion soon. So the other key notion is agency. So we have in mind 3 necessary conditions for agency. So the first condition is that the agent must be able to create a world model, a model of their environment. Secondly, the agent must be able to use the world model to evaluate the likely consequences of alternative actions. And I'll illustrate that in detail in a moment. And then finally, the agent must be able to perform the action which leads to the highest expected utility, basically the best option from their subjective perspective. Okay, so I'll unpack all of that in a moment, but just while we've got that there, we can just reformulate the question. Can a purely quantum system satisfy the 3 agency conditions? So that's our question, and here's what we're going to try and convince you of. We're going to try to convince you that the answer is no. The way in which we'll do that, I'll spend the first 20 minutes unpacking the agency conditions, and then I'll hand things over to Emily, who's going to explain why a purely quantum system isn't going to be able to satisfy those conditions very well. And then it'll get passed over to Kai, who's going to illustrate these points with some concrete examples, with some actual quantum circuitry, quantum agent circuits. Okay, just before I unpack the agency notion, it's perhaps worth addressing an objection that we sometimes get, at least early on in the discussion, which is, why do this? Because some people might look at this and think, hold on, isn't that just obvious? Isn't it just obvious that an agent is a classical thing and couldn't possibly be this purely quantum thing? Perhaps, but let me just address that by talking about the way that we're thinking about the significance of this result. So first of all, so if we're right, if we're correct in this result, the impossibility of pure quantum agents would place constraints on the physical requirements for agency. So although it might seem obvious that agents are necessarily these classical beings composed in a particular way, we don't really know. We are still trying to figure out the physical basis of agency and related concepts like consciousness. So this feeds into that project of putting constraints on the possible types of physical systems that could be agents. Relatedly, based on this analysis, we can define the classical limit of agency and show how classical agents emerge in the quantum universe. So if you're interested in emergence at all, how things in the macro realm emerge out of an otherwise quantum universe, this is playing into that project. You'll be able to see this, especially when Kai presents some of these quantum agency circuits, because you can see what's failing with them with respect to agential behavior, but then you can also see precisely what classical components you need to add in order to get agency emerging in an otherwise quantum universe. Thirdly, something that's close to my heart, the result challenges several contemporary theories of free will and consciousness. So although you might think these things are just obviously classical, a lot of people don't find that obvious, and there is a whole cottage industry dedicated to quantum theories of free will, quantum theories of consciousness. So very briefly, you're probably familiar with free will debates, where some people believe that if the universe is purely deterministic, like a classical universe, then we don't have free will. Some people respond to that by saying, okay, we don't have free will then. Other people say, well, maybe the universe is not fully deterministic. And then they appeal perhaps to quantum mechanics because it's not fully deterministic on many interpretations. And so maybe the speculation goes, there's a little bit of quantum mechanics going on in our agency, and that's somehow playing a role in giving us free will. So there's a lot to say about how you could spell an actual full-blown theory like that out. Our results, we believe, put serious constraints on the development of such a model. Such a model would have to be a hybrid classical quantum model, and it will put constraints on exactly where you put the classicality. Similarly with theories of consciousness, I won't say too much about it, but maybe you've heard of Roger Penrose, Stuart Hameroff, who believe that if you want to understand consciousness, you've got to go further, deeper down than neurons. You've got to look at quantum computations inside microtubules. And then ironically, some people argue that consciousness must be quantum on the basis of the no cloning theorem, which we're using to reach the opposite conclusion. So some people think the solution to the problem of other minds in philosophy, why it is that we don't know exactly what it's like to be someone else, what it's like to be a bat or an octopus, why we can't derive from the physical state of an AI, whether it's conscious and what the character of its conscious is. Some people say, well, why would that be? And they try to explain that by saying, well, it's because you can't copy or clone the information about the experience. And so they draw the conclusion that experience must be quantum. Okay, those are just some examples. I could probably spend half the talk going through different theories like that. These results are meant to constrain those sorts of approaches. And then finally, perhaps there's a technological constraint. So obviously people are very interested in simulating agents. People are also very interested in quantum computers. These two things are going to converge. People are going to be interested in simulating agents with quantum computers. These results, we think, might put constraints on that. Okay, so hopefully that's enough to make you care at least a little bit about these results. So let's jump into it. So our notion of agency. So we start with this idea of a world model, which is an internal representation of the external world and one's place in it. Agents use world models to assess the likely consequences of their actions, to decide which action to take. And perhaps it's helpful to use an example, a mundane example. So this example, you can relate to this example a bit better if you imagine that you don't have a car and that Uber is not available. So what you're deliberating between is whether or not you should walk to campus or take the bus.
So you consider an agent as books. So that's not a sharper student.
This is me.
I know.
Yes. Well, we think this is Emily. The reason, the way that I came up with this image is I put our essay up until this point into Panther AI, the image generator in Panther AI, and I just said, can you give us an image that illustrates the deliberation process here? And that's the first thing it spat out, which was reasonable.
You also have to assume it rains.
They can get the campus either.
This is not relevant to.
Oh, all right.
Apparently brains underneath your umbrellas.
Where else? Yeah, it's a far away. Okay, well, it did pretty well there. Okay, so here's a deliberation process being illustrated. And the idea is that there's a world model. Maybe there's a model of the route to campus. Maybe that's just, the pathway in both cases. But the idea is if one is going to deliberate between walking versus taking the bus, one needs to sort of transform these world models. So they're going to need to make copies of these world models. And in one case, figure out the consequences of walking. And in this other case, take the other copy of the world model and figure out the consequences of taking the bus. Then one wants to weight those consequences, evaluate the utility of those consequences, and go with the best option. Okay, so is it a clarificatory question?
Yeah, I'm just curious. Under this definition of an agent, would a chess engine count as an agent?
Possibly. I'll come to that.
Yeah, because
We're getting
curious the scope of the definition.
Yeah, this is what my presentation is all about, the scope. So
Sorry, another question that can appear a joke, but in fact it is not a joke, I think. A soccer player in any instant has to take a decision whether to do one thing or another. But that decision, if he's good soccer player, should be taken in so short time that there is no time to evaluate different circumstances and compare one to the other. And the great difference between a good soccer player and a bad soccer player is that a good soccer player is able to make the good decision without evaluating all circumstances. Otherwise, if a soccer player could evaluate all circumstances, one could be good. So a soccer player in these circumstances is an agent. It takes a decision, but it does not take a decision based on the real evaluation of different possibility or a world model.
okay, yeah, I'll present some concepts relevant to that very soon. So we can model this process with decision theory. So especially subjective utility theory coming from Savage. So the idea is that the agent forms a representation R of the environment and then makes copies, a set of copies of this representation, where each copy is linked to a possible action. And then for each copy corresponding to each action, the agent predicts possible outcomes and assigns probabilities to these outcomes. This is representing an agent under some uncertainty. So for example, when the agent is figuring out the consequences of walking, they might not know exactly what the consequence will be because maybe they don't know, for example, exactly whether or not it's going to rain. So they'll assign a probability to that. And so they've got different outcomes corresponding to the same action, and they're assigning probabilities to it. They can also assign utilities to those outcomes conditional on the action and calculate the expected utility. So for example, if you're calculating the expected utility of walking to campus, maybe you've in your world model's got information that there's a 0.8 chance it's going to rain, a 0.2 chance that it's not going to rain, and maybe if it rains, that's a really bad consequence. So the utility is like, I don't know, -10. Otherwise, the utility is +10. So then you get 0.8 times -10 plus 0.2 times 10, which is -6, which is bad utility. So that's bad, and that's probably going to be a lower utility than the alternative of taking the bus. And so probably you're going to take the action with the highest expected utility and take the bus. Okay, so this is a little bit of an idealization. It's not exactly that we calculate these exact values, and we don't need to make that assumption. Nonetheless, this captures the form of, or the general form of deliberation, which we care about, and we especially emphasize this copying going on here. And in what follows, we're also going to simplify a little bit and imagine that our agents are certain of the consequences of their actions. So we're not going to worry too much about the sum and the probabilities here, but the utilities are certainly relevant. Okay, I'm very close to being able to address the two questions that I had.
What is the role of the copy?
The role of the copy.
Yes.
So I want to evaluate the consequences of different actions in this one world that's being modeled. So I'll need one model to evaluate the consequences of doing one action. I'll need a copy of the model to evaluate the consequences of doing a different action. And then I deliberate between the two.
Why do you need a copy for that?
Why do I need a copy?
This is what Aristotle would call analysis. The idea when you take a vacant deliberation, what you know is to consider the world with the certain consequences, and without a certain consequences, it's
Briefly.
I mean, one reason you might not need a copy is you imagine you have to take this world model and do some computation. The results of that computation is expected utility of that dimension. Okay. In principle, computation can be done reversibly. Right, so we do the computation reversibly, take out the answer, put it to one side, undo the computation, and then you're back to the original copy. So if you do it like that, it seems like you don't need to make copies.
If you're reversing the calculation, does that mean that you forget it?
It doesn't. I mean, you save a copy of the answer and then you undo.
But if you save the copy of the answer, don't you have the copy?
This is how it's done in quantum computing. So that you start with a state, you run your computation, you copy the output, something, then you undo the computation reversibly back to the original state. You save erasure costs. And you can always like copy the output of the calculation without compromising the reversal.
Do you think it's plausible that we are doing this reversal when we're
No, of course not. I just, and this is an in principle negative theorem.
fair enough?
What, like, when we say copy, do we mean like perfect copy? Because I feel like when we create world models in our head, they're not like an exact copy.
Yeah, so for now, it's easier to just think of a perfect copy. And we're going to grant that to the quantum agent and see what happens if we allow that, there's not some coarse-grained sort of extracting of information, but we allow in principle, they could get a perfect copy. So you'll see all this during the talk. We use something called a swap sensation that just swaps in the environment so that you get an exact copy of the environment state. But yeah, we'll get there. One more, and then I need to.
So we're going on about only this thing should in the end, we are arguing that this cannot be done in the purely quantum, right? So is this copying the output to memorize it to quantum operation?
Yes. So
Okay.
yeah, this is a side thing. Let me explain that after the talk.
Okay, so let me continue. So condition one, obtaining a world model requires copying of information from the external world. So that's the first part, involves copying from the external world. And then we've got this second part that I've been highlighting, where using the world model to deliberate requires copying the world model to evaluate multiple actions in parallel. And then the third condition is that the agent must select the best option. And that just can be the best from the subjective point of view of the agent. So what we want to argue is that conditions 1 and 2 are going to fail in a purely quantum setting due to the no cloning theorem. And then condition 3 is going to fail for a different reason, and it's going to be due to the linearity of the dynamics governing the quantum agent's deliberation. Okay, so in a moment, Emily's going to explain why it is that these 3 conditions are hard to meet. But what I'll do just to finish is try to consider some of these objections about why we're using particularly this notion of agency as opposed to some other. Okay, so other notions of agency. So if you look at other fields, many fields are studying agency, and different fields often attribute agency to very simple systems that seem far too simple to exhibit the conditions that we talked about. So in biology, for example, Michael Levin has been getting a bit of attention by saying you're actually a hierarchy of agents. You're an agent composed of many agents, agency all throughout your body. A nice example is memories can count as agents. And perhaps a simple way to see that would be to think about like a traumatic memory, one that you'd like to just get rid of, but it's kind of got a life of its own and it's sort of not going away. It's kind of trying to preserve itself in a way. It's acting so as to preserve its own existence in your brain, kind of a homeostasis. And some people think that's what's really important to agency. In artificial intelligence, and this is a well-known AI textbook, Russell and Norvig, they say that even thermostats can be agents. But it seems like thermostats aren't doing the kind of deliberation process that we've been talking about. Nonetheless, Russell and Norvig, they do have this helpful categorization scheme where they give us 5 different levels of agency. And so when they're talking about thermostats, they're just talking about what they call simple reflex agents. And this is a model that they use for a simple reflex agent. Here's the agent. It's got some sensors, which take some perceptions from the environment that enables it to know what the environment is like just right now. And then it's got some condition action rules that says, okay, given that that's what the environment is like right now, here's how I'm going to act. So a thermostat is like that. I like the example of a robot vacuum just because they kind of sometimes look like little agents when they're doing their thing. You know, if there's a barrier, then do a big twirl and go in a different direction. Condition action rules. And then at each stage, we make these things more sophisticated. So the next level is the model-based reflex agent. So now we add a world model, but it's still not at the level of deliberation that we were talking about. So just take the robot vacuum, for example, and give it some memory of where it's been. And you can imagine that its condition action rules take into account this model of where it's been, so it doesn't vacuum places that it's already vacuumed. Then we move up to goal-based agents, and this is where we think the copying becomes relevant. So to illustrate a goal-based agent, you can just imagine a self-driving car, for example. So it's got a goal, which is to get a passenger to this particular address. And they might consider different options. So they've got a world model, which might just be a model of the city. And then they go through different routes, different possible ways of getting there. And then as soon as one meets a condition of getting there on time, it just selects that option. And then going up to really what we're talking about, the utility-based agents, is where, just to use the self-driving car analogy again, the self-driving car now scores the different routes. So it scores the different routes based on how fast it gets there, maybe how dangerous the route is, other things. So it's assigning utilities. And so it's weighting, and then it's going with the better option. So we're really talking about utility-based agents. Learning-based agents is another thing that perhaps we'll come to in later research.
Sorry, there is something that I don't understand. That is, it seems to me that in this hierarchy, with the exception of the first case, thermostat, it is certainly an agent very, very simple. All is required in order to be an agent of another system to have a model, be able to construct and to explore. I think that to be an agent does not necessarily require to be a model. The example of the soccer player is one, but the example of each of us.
Yeah.
I don't when you decide that you drink, because you are not compare different model, you are not really comparing situation which you drink with situation which you not drink.
Yep.
You simply have a certain habit, you have a certain experience, you go. So the idea of the model seems to be quite.
So I have one more slide left. I'm hoping it's going to answer it, because my final slide that I'll present is going to tell us why we care about this type of agent. And one thing that we don't want to do is fight over words. So we don't want to say, hey, don't call that an agent, don't call this an agent just because it doesn't satisfy our conditions. That's sort of not the goal here. What we do want to motivate is not that this is the one true definition of agency, but this is perhaps the most interesting notion of agency for our task. We're particularly interested in the kind of agency that we have. So let me just pull together a few arguments for why that's the interesting notion of agency. And so I'll try and just pull some considerations from a few different sciences here. So in psychology and also in neuroscience, they've been studying recently something called the sense of agency. And so we have a kind of sense of agency, a sense of control over our actions, a sense of volition. And one reason this has been studied more recently in psychology and neuroscience is because there's ways of measuring it that don't involve just explicitly asking a subject to tell us to the extent to which they feel like they have agency. There are implicit measures of one's sense of agency. So there are more objective ways of studying this. And Klikova et al. Found that our sense of agency was strongest when participants had alternative actions leading to different possible outcomes. So connecting our notion of agency to our sense of agency. Similarly, in neuroscience, Haggard found that our sense of agency is associated with the dorsolateral prefrontal cortex activity, which is a brain region involved in selecting among alternative actions. So if you damage or lesion that part of the brain, then someone's going to not do very well with selecting among alternative actions. In philosophy, I think our notion is the important one as well. So in philosophy, this connects to free will and also to moral responsibility. And so philosophers are looking at the requirements for those things. And we think that in general, the requirements that we've put forward are necessary for the typical analyses of free will and moral responsibility in philosophy. So I just pick out a few candidate examples, the libertarian Kane and two different schools of compatibilism. So they try to give conditions for free will, conditions for moral responsibility, and we think they at least involve our conditions and perhaps some additional conditions. And then finally, some recent research in AI that we've just come across, some results from Richens et al., which try to prove that any agent capable of generalizing to a sufficiently wide range of environments or goal-directed tasks must have learned an accurate predictive model of its environment. So if we set aside just lookup tables, which for sufficiently complex environments and sufficiently complex goals is not going to be efficient, then basically you can look at the behavior of these agents and sort of derive an accurate world model, suggesting that that's going to be the best explanation of why they are successful in their environment. Okay, so there's a bunch of reasons from a bunch of different places to suggest that this notion of agency is an important one to consider. And so it's a good one to ask with respect to purely quantum agents. And with that said, I'll pass things over to
So
you.
your point in the end of the story is that quantum system is not a world model agent.
Yeah.
Possibly could be utility agent, but not this one.
One thing before everyone starts up, just to answer your soccer question. If you have a utility-based agent that could model learning how to play soccer correctly. And then once you've ingrained those lessons, those things become sort of the reflex agent part that's built into you. So there's a hierarchy process where you can transfer from one to another.
This is clear. Okay.
I mean, our claim is not necessarily that a human uses this process every time that they make a decision, but that part of being an agent like us is having the ability to do this in appropriate circumstances. Okay, so having set out the conditions for what we think is an interesting notion of agency, we want to ask, can this type of agency be implemented by what we call a purely quantum agent? So here we're focused on the purely quantum system, which, as we've said, is a unitarily evolving system in a quantum regime. And I'm going to focus here on the case where that system is also immersed in a quantum environment. We do think that these results would also generalize in interesting ways to the case where you have a quantum agent immersed in a classical environment, but I won't talk about that right now. We can always come back to that in the discussion. So in particular, I'll take this to mean that there is no preferred basis either in the system or the environment. So in a classical environment, for example, systems can reliably be found with well-defined positions. That is, they're found to have well-defined state in the preferred basis, which is the coarse-grained position basis. So classically, we're used to dealing with a preferred basis. So I'll take it that our quantum agent does not exist in a situation with a preferred basis like this. It's defined by an environment of quantum states that could be drawn from any basis, and the system doesn't have any information about what that is going to look like. In the classical case, the reason we have a preferred basis could be because of wave function collapses, could be because of decoherence in the Everettian context or something like that. We're going to rule out those kinds of processes for the moment and focus on an agent existing in a regime without any of those things. So there's no preferred basis, and you can't expect that the states surrounding you are going to be in any particular basis. So what I want to do now is go through each of these conditions and show that there are significant obstacles to our purely quantum system implementing what we've asked for in terms of each of these conditions. So first off, our first condition was that obtaining a world model requires copying information from the external world. It's a fairly sort of standard process that we go through. We see something happening in the external world, we make a copy of that in our brains, and then we use that to do various kinds of deliberations. So in the classical case, that is fairly trivial, and we assume that we can observe the external world without disturbing it and without taking anything out of it. In the quantum case, that becomes much more complex. In particular, because it's a quantum environment, the system is surrounded by unknown quantum states. And that means the no cloning theorem applies. So the quantum no cloning theorem just says that there does not exist any quantum operation which can perfectly and reliably copy an arbitrary quantum state. So if I give you some quantum state without telling you anything about what basis I prepared it in or giving you other information, there's nothing you can possibly do to reliably produce a perfect copy of that. So that is just a general result which applies straightforwardly to any case where you're dealing with a completely unknown quantum state. What that means is that our quantum agent, which does not have a preferred basis around it, which doesn't know anything about the basis with which the environment states have been prepared, is not in general going to be able to copy information out of the external world.
But it does not follow from the theorem as you present, you cannot perfectly copy.
Yeah, I'm going to deal with
perfectly copy,
Marco.
does not follow that you cannot copy.
Yeah, Marco, I'm going to come to imperfect copying in a minute. So of course, our agent could simply remove a piece of information from the environment. So that's what our colleagues in Toronto have proposed with their work on quantum agency, that you could just swap a state in from the environment and have that in your brain. And of course, it is possible, always possible to do that. But if you do that, then the state that you took into your brain is gone from the environment. And there's sort of no longer any point really in using that thing to model the environment because it's not in the environment anymore. So doing swap operations is not going to be a useful thing to do unless you have some good reason to expect that most of the states in the environment are in the same state or very similar or related states in some sense. So was that a question?
Yeah, what is exactly this swap operation?
Swap operation involves the state and the environment. I also have a state on the same dimension in my brain. I just swap them. So I put a piece of my brain out into the environment to take a piece of the environment.
You swap, you put something in the environment and you take that thing of the environment in your mind.
Internal, I mean, it's state, right? So you have a system of the same type somewhere in your head, and you just swap the states of those two things.
So you change the environment. Okay.
This is you're taking a state out of the environment and putting a different state back into it.
I see.
So whatever you took from the environment is now gone. So whatever model you do with what you've taken from the environment is not going to tell you anything useful about what is now in the environment because it's gone. Yes.
So just a quick clarification. Why is your agent so ignorant about what it's modeling? Because usually an agent has significant knowledge about what it's trying to model, but here your agent knows nothing about anything, it seems. So why?
Well, the agent needs to take in information about the current state of the world now. So as an human agent existing in the world, we do have background information, but then we're interested in going out into the world and trying to learn what is the state now and using that to do some modeling. So that's what the agent is doing now. It's taking information about the current state of its environment. We're not going to allow it to have knowledge of a preferred basis because in that case it wouldn't be a quantum environment any longer.
You're saying that the agent can have internal knowledge somehow, but it's the act of taking in new information that is restricted.
Yeah, it's the process of learning what is the state of my environment right now.
Is the nature of the swap operation is such that once you do the swap, that you lose memory of the state of the thing that
you lose whatever you put into the environment.
Yeah, right.
But you could have a bunch of spare states that you're not using in your brain. So that's kind of okay. But the worry is that what you've taken from the environment is gone now. So it's no use to use that for modeling. Makes sense?
Yeah, but you also can't then do that like an infinite number of times and then have perfect knowledge of the environment because you don't know the states anymore once they're.
Well, you could do that an infinite number of times and then you would have perfect knowledge of whatever used to be in the environment, but it's all gone now because you've moved away. So you've learned nothing really about what's out there now.
Yeah.
Great. Okay, so if we still want to try to implement some kind of agency in the quantum context, what can we do? One option is the agent can do various kinds of imperfect cloning. I'll talk about those in a minute. And the other option is that we're just going to be kind to our agent and suppose that it's in some kind of special case where the environment is a bit more friendly to agency than the sort of general case where it's completely unknown. So we can, for example, consider a special case where we give the agent a guarantee that there's going to be 2 copies of the same state in its immediate environment. In that case, we can do the swap operation, take one of those states into the brain, leave the other one in the environment. So the agent can then do some modeling and decide how it will act on the other state. Is that a realistic case? It's not obvious to me how that would arise, But nonetheless, let's allow the agent to have that advantage for the moment. The point of what we're going to do here is we intend to show that even if the system is given this advantage, so it has this special knowledge of something two identical quantum states in its environment, even in that case, it's still not going to be a very successful quantum agent. Right, so I'll talk in a minute about imperfect cloning, but I now want to talk about the second place where we think cloning is necessary in the operation of agency, and that's the idea of using the world model to deliberate. So the thought is that using the world model to deliberate is going to require copying the state that you've taken in from the environment to perform several different computations on it. And we can see that the no cloning theorem is going to be a problem here, because if you imagine you had a process where you take in a single state from the environment, perform several computations and get several distinct outputs out, what you could then do would be just reverse them all and get back the original state, and then you would have cloned that state. So that can't be possible. It must be some limitation on the extent to which agents can do parallel computations like that on the same state and get out distinct independent outcomes. So again, no cloning is going to be a problem for the agent here. It looks as though the agent is not going to be able to perform lots of different calculations on just one copy of the environmental state. And so what you might think here is that if you have a quantum agent, what you could do is take your one copy of the state and then perform some superposition of different operations on it at the same time. That's sort of supposed to be the advantage of quantum computers, that you can run several computations in parallel. And certainly you can do that, but the problem you're going to have is that the result of that is just a sum of various terms corresponding to the different operations you've performed. And sums are, of course, commutative. So if you're just looking at that final state and you don't have information about what the original state is, there's no straightforward way to figure out which of those terms came from which operation. So you can't use that to assess which operation was more successful. Although you can do operations in parallel, and a quantum computer doesn't seem like you're going to be able to use that to usefully assess what is a good action to do in this case. So what can the agent do? So again, the agent could do some form of imperfect cloning. What we'll see in a minute is that imperfect cloning becomes more and more imperfect as you try to produce more copies. So that means that the more actions that the agent wants to deliberate over, the worse those copies are going to get. And eventually the copies are going to end up containing almost no information about the original state. So what we see is that there's some quite strong limitations on the extent to which our quantum agent can meaningfully consider lots of different actions, because the more actions you try to consider, the worse the model it gets. So again, sorry, yes.
Oh, just a clarification. This is the condition that I'm just not sure I understand why we need it a priori. Like, you're just talking about an agent in general, whether it's quantum or otherwise.
Yeah.
Why do you need to copy the world model? Why not just run it twice? I mean, conscious deliberations are uniformly serial. You can only deliberate consciously about one kind of state of events or state of affairs at a time. So you typically would think about one, compute consciously the expected value, and then now think about the other one. You do them in series. So I'm not sure why you need to copy them.
Because if you were able to do several different computations in a row and keep all the outcomes of those computations, so now I've got, I don't know, 8 outputs that I produced. Now I can just reverse all of them using the same unitaries I used to produce them, and now I've got 8 copies of the input state. That's not possible. That's cloning. So this is because this is a completely unitary regime. We can't have a situation like that where you produce all the 8 outputs, because everything can be reversed back to the original state. Does that make sense?
No, but I'll hold it from there.
It's basically because if we could do what you're saying, that would make it possible to perform cloning.
But we do what I'm saying.
Well, yes, because we live in a classical regime. We are not quantum agents. So when you do the same computation many times, that's because you're a classical agent and we can copy things classically.
But that's what I meant. Isn't this an a priori condition that any agent needs to satisfy it, regardless of whether it's quantum or not? You started with this as just talk about agents. This is a condition that agents have to satisfy.
Yes. And so my claim is that when you do what you're describing, what you're in fact doing is creating copies of the information in the state and using them to do different computations. And that is a straightforward thing to do classically, because classically copying information is easy. We don't even really notice that we're copying information classically because it's free. It doesn't cost anything. It's only when you move into the quantum regime where there's a limitation on copying that you realize that doing a bunch of different computations and keeping the results requires copying the input several times. if you have a classical register and you have some number in it and you're going to do several computations on it, you take a copy of that number, you put it into computation one, you get an output, and you go back to the register, take another copy, and do that again. That is a process of copying, and in the quantum regime, that would be cloning. Great. So because that's going to cause problems for our agent, we're again going to be kind to our agent and suppose that it exists in a sort of special case where the environment contains many copies of the same state. In that special case, our agent doesn't have to try to copy or clone because it can just take a number of different states from the environment. However many actions it wants to consider, it can just do that many swaps, take in a number of copies of that state, do its modeling, and then produce whatever its output is. So again, I'm not sure this is a very realistic scenario, but we're going to be kind to the agent and give this advantage, and we're going to see there are still significant obstacles to actually implementing agency. Okay, so I'll talk about condition 3 in a moment. I just want to briefly do a digression into some methods of imperfect cloning, which the agent might appeal to in these kinds of cases. There are 3 important types of imperfect cloning that have been discussed in the quantum foundation literature. The first is state-dependent cloning. So that applies when the state that you're given is not completely unknown. Rather, you're told that the state is going to come from some specific set of states. In that case, it's possible to design optimal cloning operations which will produce the best possible clone for that particular set of states. So usually that is going to be better than what you could do by just performing the generic cloning operation. In particular, if you know that the state is going to come from some set of mutually orthogonal states, in that case you can do perfect cloning, but that of course is just the case where there's a preferred basis. That's not the case we're dealing with here, but if there was some other type of restriction on the class of states, you could potentially have cloning that's better than generic cloning, but still not perfect. Second possibility is what's known as probabilistic exact cloning. This involves a unitary operation together with a measurement, which with some probability p succeeds in cloning an input state. This does only work if the states that you're starting with are linearly independent. So again, there has to be some kind of restriction, but it does, with a certain possibility, produce a perfect clone. Third option is deterministic imperfect cloning. That involves a unitary operation which takes n copies of a qubit or larger dimensional state in some fixed unknown state and produces a set of m outputs which are supposed to be close to the original state according to the fidelity measure. Now, in our case, if we assume that the environment is indeed completely unknown, then state-dependent cloning is not going to be helpful to us. Probabilistic exact cloning is not available because it requires a collapse. We're not allowing collapse. It would also require a restriction to linearly independent states. So deterministic imperfect cloning is an option, and this is probably what the agent would have to do if it's not being given the special case where there are lots of copies in the environment. So this can be done, but it does lead to quite significant losses of information. So in particular, if you consider symmetric universal n-to-m cloning for qubits, so taking in n copies of the same qubit state and trying to produce m output copies, it's symmetric in the sense that all of the resulting outputs are supposed to be the same, and it's universal in the sense that it's supposed to work on any possible input states. And considering the 1-to-2 case, so one copy trying to produce 2 copies, what we can do is map that input state psi to 2 systems with a density matrix, which is a sum of psi plus a state which is orthogonal to psi. And the fidelity of that process is going to be 5/6. Now, fidelity runs from 0 to 1, so you might at first think, well, 5/6 is pretty good. But we should keep in mind that in this case, we can always get fidelity 3/4 just by leaving the input state alone and then preparing another state at random. The average fidelity then across those 2 states is 3/4. But 5/6 is not that much bigger than 3/4, so you can see that actually we're not doing that well in terms of fidelity in that case. And certainly as you try to produce more and more copies, the fidelity goes down quite quickly. For 1 to 4, we're already down to average fidelity 3/4, which was not better than what they're guessing at random case for the 2-qubit case scenario. So you can see that the information goes down pretty quickly, and as you try to produce more and more copies, you are losing most of the information you're interested in modeling from the environment. So deterministic imperfect cloning is an option. Kai is going to talk some more about some quantitative examples with that, but we can see that as an approach to agency, that is going to have some significant disadvantages.
Can you explain better why you dismiss the first possibility?
So state-dependent cloning is a case where you're told that the state is going to come from some set of restricted states. So you have some information about what kind of state it's going to be. The case we started with is a case where the environment is completely unknown, so we don't have that kind of information. If you want to consider a special case in which the agent is told that the environment state is going to come from some set, you can certainly do that. That's not the case we're talking about here. Certainly, you won't be able to get, because we have specified there's no preferred basis, that means you're never going to have the perfect case, because that would be the preferred basis case.
Exactly what an agent do is consider what is relevant and what is not relevant. And of course, there are a lot of things that she does not know if it be relevant. It's exactly the work of the agent, considering what is relevant and not relevant with evaluation. I can be wrong, of course, but the thing is, an agent is someone that can be wrong.
This is not up to the agent. This is for state-dependent cloning. You need to guarantee that the environment will produce certain kinds of states. There might be some cases in which the agent happens to be in an environment which has certain kinds of states, and so you would have to set up a scenario in which, for some reason, the states are being produced from some particular set. Certainly, that's a possible thing you can imagine, and perhaps that would make life easier for the quantum agent. But what I would say is that basically, once you start doing that, you're moving more towards the classical regime. The classical limit is basically the limit in which we go towards all the states coming from the same preferred basis. So putting that kind of restriction essentially involves moving away from the quantum case and towards the classical case. Right, okay, so condition 3. Let's suppose that we have given our agent unlimited copies of the environment state, so it can take in as many as it wants, it can test out as many unitary operations as it wants, and it now arrives at a set of output states, which is going to have to evaluate to decide what action it wants to perform. So condition 3 requires that the agent should be able to select and implement the best option. Classically, that seems quite straightforward. Once you've done all your modeling, you just look at the outputs, you decide which one you like the best, and then you perform the corresponding action. Whereas in the quantum case, we're going to see that turns out to be much more difficult, and the agent cannot reliably actually do that. So for straightforwardness, we're going to suppose that the agent has a fixed goal. The goal of the agent is to transform its environment state to a quantum state which is as close as possible to some fixed state 0. So what it's going to be doing here is looking at the outputs of all of its models, seeing how close they are to 0, and then implementing the one that gets closest to 0. So in order to fulfill our condition, the agent would have to be able to reliably see which one is closest to 0 and perform that one on the environment state. We're going to see that, in fact, it can't reliably do that. So first off, note that the agent can't measure its results since it is a purely unitary agent. That means we're going to require some unitary operation which acts on the results of all of the modeling, chooses the one which is closest to the desired target state, and then implements the corresponding operation on the target qubit. And in fact, we can see that there is no unitary operation which reliably achieves this for arbitrary states. In addition, we will show that the target qubit will typically end up entangled with the modeling qubits, so you don't even get the desired outcome of a sort of pure state in the environment. You just end up entangled with your environment state in complicated ways. So the proof for this, the impossibility of this operation is somewhat similar to the no cloning proof, if you're familiar with it. Basically, what we're going to do is consider if this operation did exist, how would it have to act on various possible basis states, and we'll then appeal to linearity to show that it's not possible that it has the desired action on all arbitrary input states. So first off, let's suppose the agent has made 2 copies of the environment state that it took into itself, and it's tried some operation U1 on the first copy, and it's tried some operation U2 on the second copy. So U1 has produced some state A0 plus B1, U2 has produced some other state C0 plus D1. And what we want to do now is design an operation which performs either U1 or U2 on the target, depending on which one of them has produced an output closer to 0. So basically, if the absolute value of A is greater than the absolute value of C, we should perform U1, otherwise we should perform U2. So we can see that this operation is going to have to act as follows on various basis states. The first, if U1 produces a 0 and U2 produces a 1, then that tells us that U1 was a better operation, so we should be performing U1 on the target here. If instead U1 produces state 1 and U2 produces state 0, that tells us that U2 has done better, and therefore we should implement U2 on the target state. If both U1 and U2 produce 0, or both U1 and U2 produce 1, then they're either equally good or equally bad. So there's various options for what you might have your agent do in this case. Maybe it should just implement U1 by default. Maybe it should do some mixture of U1 or U2. Maybe it should pick one at random. For the purpose of this proof, we won't decide. We'll just say the first one is going to do something that will indicate by question mark, and the other one will do something else that will indicate by question mark prime. Finally, if we have some arbitrary superposition on each of our two output states, we know that when the absolute value of A is greater, we should be applying U1 to the target, and otherwise we should be applying U2. Great. So we can now appeal to linearity. We can see that given the specified action on the 4 basis states, when we get this arbitrary superposition, the operation is going to have to act as follows, giving us this sum of 4 different terms. So in the case where the absolute value of A is greater than or equal to C, we want all of this, this long sum to come to something times U1 on the final state. So that tells us that the other 3 terms, which don't look like they have a U1 in them, are going to have to kind of cancel out in some way to give us a U1 at the end. Moreover, we know that this controlled unitary must map the 4 orthogonal control states to 4 other orthogonal states. So each of the terms in this the sum here are necessarily mutually orthogonal to each other. So the question is, can we choose question mark and question mark prime so that this expression is satisfied? So we're going to have to get rid of this 1, 0, U2 term somehow. So one way to do that is to try to cancel it out using the question mark state. So that means the question mark state is going to have 1, 0 on the first 2 qubits in order that we can add it together with whatever happened on the last qubit to get hopefully U1. And because of the orthogonality requirement, that tells us that question mark is going to have to be 1, 0, and then some other state U2, which is orthogonal to the state U2 here. So that we can then substitute that into this expression. We're going to add these 2 things together. We're going to get 1, 0 on the outside plus some combination of A plus B on the final target state. And we want that combination of stuff on the final target state to give us the state at the end. So you can see that one way to make that work is to set C equals 0. So 0, 0 equals 0. The other possibility is to make the stuff inside the brackets add up to U1. And there will be a way to do that. There's certain choices that you can make. So specifically in that case, we're going to have to set U2 equals 0, U2 orthogonal equals 1, and so we're going to get C equals 1. So if C equals 0 or C equals 1, we can make this work, but for all the other values of C, it's not going to work. The alternative is to use the other question mark prime to try to get the same kind of result. So again, we're going to have a 1, 0 on the first two qubits, and then something orthogonal to U2 on the third qubit. Substituting that into the expression that we will have here, we can again see that either we can make B equals 0, or we can make the stuff inside the brackets equal U1. And again, substituting that in and rearranging, we see that in that case, we're going to have A equals C squared plus D squared equals 1, and B is going to have to be equal to D times C minus C star. Moreover, we can always choose the global phase, so we can make the imaginary part of C equal to 0, in which case we can see that B is going to be equal to 0. So again, this will work if B equals 0. It's not going to work for arbitrary values of those coefficients. So what we see here is that although it's possible to make this operation work in a couple of very specific cases, there's no operation that is going to work generically for any possible set of inputs. Great, so in conclusion, there is no operation which reliably and chooses and implements the most successful operation out of the options that the agent has tested. So even in the best possible case where we gave the agent all of these copies of the state it's supposed to be thinking about, it still can't really do very well as an agent. In this case, it might be able to produce a model which does, as a matter of fact, kind of establish what the best action will be, but it can't generically recognize and then just implement that action in the way that a classical agent would. And we're shortly going to see some examples showing that, as a matter of fact, the target will usually end up entangled with the control qubits. So you were trying to produce a pure state in the environment. Instead, you end up producing some kind of mixed state that is entangled with your control qubits in various ways. So I'm going to hand over to Kai now, who's going to present some of the more quantitative thoughts. Yes, sorry.
Why are we eliminating the idea of it just returning a mixed state based on relative values of the two solution. So it doesn't seem unreasonable to be like, I think 90% of the time, one decision would be better, and 10% of the time, the other would be better. For me to do one 90% of the time, the other 10.
Well,
That's
okay.
perfectly.
In the case that we've considered, there's always a fact of the matter about what is the best operation, because the goal is just to produce a certain state. So one of them is going to be closest to that state. We actually don't necessarily rule out the possibility of producing a mixed state. You know, Kai is going to present some results showing how close you can get to the target state if you have mixed states. And the answer is you can make some progress, but it's not overall very good. Yeah.
There is a target state. Why is it not always just in the 1, 0, 0, 1? The generic case, if there's one that's clearly bad decision.
Because your unitaries aren't necessarily going to give you 0 or 1, and because you don't know what the input state is, unless you can consider an infinite number of unitaries, you're not going to be guaranteed that one of your unitaries actually produces 0 or 1. Because it could have been any state from the whole block sphere that you had as an input, so you don't know which one is going to, you don't know which operation to try. Does that make sense?
All right, so Emily pretty much just explained what we're going to do to construct a unitary quantum agent. We're going to just build a unitary that implements both the deliberation steps and the action on the environment state. So to really mimic what Kelvin was talking about, where we're actually getting some input from the environment and then actually doing something back on the environment, we're going to sense the environment by swapping in the qubit state. We've already talked about that. And then we're going to do some, I'm skipping a step here. In general, if the state of the qubit that was in my brain was already entangled with other qubits that were in my brain, or if the state of the qubit that was in the environment was already entangled with other qubits in the environment, then just doing the swap operation will entangle the environment with the brain. So that's what happens in general, but we're going to consider the special case where both of them start off not entangled to anything else. So I could just do a clean swap of the two. But more generally, you have to consider that other possibility. So the agent's goal is to swap in the state from the environment, do this deliberation and action operation on it to put it as close to the state 0 as they can, and then swap it back into the environment. This is kind of a silly generic example, because if the agent, for example, just had a state 0 in their brain, they could just swap it into the environment and they would accomplish the goal. So in general, we would imagine more complicated goals for the agent, but this is just kind of to get a sense of the flavor of what's going on here. Okay, so to deliberate on multiple actions, we're going to want to apply unitary to each of several copies. And we know this is a problem because of the no cloning theorem. So we're going to consider 3 different scenarios altogether. So in the first scenario, we'll just talk about a classical environment. This is the case where somehow the agent knows what the basis the environment states are going to be in. And that allows the agent to make perfect clones. If you know what the basis is, you can make as many copies as you like. And so now you're in the situation that Emily was just talking about, where you have an environment that you have as many copies of the state as you want. We'll also just consider the case where the environment is quantum, the states are not in some known basis, but the environment just has many copies of the same state. So that's also kind of the case that Emily was talking about. And then finally, we'll consider a case where you just get one copy of psi from the environment. You do a swap, you have no guarantee that any other states in the environment are the same state, but you still want to be able to influence the environment in the desired way. So you're going to take your one copy and you're going to do symmetric cloning on it. Now, the symmetric cloning doesn't actually give you a bunch of separate mixed states. That's a little bit deceptive. I talked about this yesterday for the warm-up talk. It actually gives you a symmetric entangled state of all the qubits. And actually, there's also ancillas in there. So you have to trace out the ancillas, and then you end up with a symmetric mixed entangled state of all the qubits. That's what you actually get when you implement this cloning machine. Now, if you take one of the qubits and trace out all the others, you're going to get a reduced density matrix, which is of this form here. Let's see, pointer. See what I mean? And so this is just showing you that you do get, to some extent, the original state back, and then you're getting closer and closer to a maximally mixed state. You're adding more and more noise to the state as you do this. So the cloning is good in the sense that if you had some direction on the block sphere, you keep it. All of your individual copies point in the same direction, but the length of the block vector has gotten shorter. And the limit the block vector goes to 0, you just have a maximally mixed state. Maximally mixed state is just one that no matter what measurement you perform on it, it gives you 50% outcomes for your two possible outcomes. And so it contains no information. Okay, so when we do deliberation with this last case, we're not actually doing the thing we wanted. We're not taking separate copies and deliberating on each of them. what we're doing is acting the unitaries on, we're taking our deliberation unitaries, U1, U2, and so on, and we're now acting them on some of the qubits in this big symmetric entangled state. And we're going to get back some other entangled state from doing that, but we're still going to feed it into our controlled unitary to do the operation on the target. So even though we can kind of get clones in this case, we're already deviating away from what our classical agent wanted to do, which was to kind of create separate world models. Instead, we have kind of a mess of entangled world models going on. Okay, so if we take the n copy clone case, the agent will use the first n-1 of those to perform deliberation. So that'll be how many unitaries I perform. And then they'll take this controlled unitary, use the controlled or deliberation qubits as the controls for the controlled unitary, and that will dictate how that unitary acts on the target qubit. So yeah, this is what I just said. So it's gonna attempt to implement the UK that brings the copy or the clone, depending on which scenario, which of the three scenarios I'm talking about, closest to 0, and then act that on the nth qubit to bring it closest to 0. Okay, so this is the actual form of the unitary. So we have some tensor product of our deliberation unitaries that act on the first n-1 qubits. So what you see, these are pointer buttons. Yeah, okay, so here are our control unitaries, our deliberation unitaries. So, first one acts on qubit 1, the next one acts on qubit 2, and so on. And I get output states of those. And we're going to use a controlled operation where if the control bit is 0, I'll act that unitary operation, because our goal is to get our state closest to 0. So basically, the closer each one of these got to a 0 state, the larger the A coefficient in the state that Emily was showing is, the stronger that's going to be weighted in the controlled unitary. But inevitably, the controlled unitary is going to act a superposition of all of the cases that gave some amount that had 0 in the superposition. And that's why we're going to end up with entangled and mixed states, or entangled states of everything and mixed states when we trace everything out. So this controlled unitary, there really is no set roadmap for how you should construct what the controlled unitary is. You have a rough idea what it's supposed to do when you get particular states. So Emily pointed out, like if we get 1, 0 or 0, 1, we know in that case, if we get 0, 1, it should be definitely implementing unitary 1. If we get 1, 0, it should definitely be implementing unitary 2. But if we want to have more deliberation unitaries, then there's not necessarily going to be a clean answer as to which unitary we should implement based on the outcome. And when we have a case like 0, 0, Emily, sort of glossed over what was happening with the question marks states, but we can try to do something with those question mark states. So if I have a 0, 0, that means that both of the operations I was trying, but they both seem to succeed. And so for that term, maybe what I should do is actually implement a superposition of the two operations. And that introduces a wrinkle. You can't arbitrarily superpose unitaries and have the result also be a unitary, but there are special cases where you can do that. And I'll look at some cases where we do that to construct a unitary that sort of tries to be faithful, even for the cases where I don't get a clean 1, 0 or 0, 1. Okay, so to evaluate just kind of on average how well this thing is doing, I didn't integrate over the entire block sphere. I just gave it this set of 26 states. So the pluses and minuses are all independent here. And then you just consider any permutation of those states. And those give you 26 vectors that cover the block sphere in a relatively symmetric way. And so what we're doing is testing each of our quantum circuits for all 26 of these states to see how well it performs at getting the output state to be in the state 0. And for that, we'll generally have to trace the other qubits out so we can compare the output state we had, even if there was some entanglement going on, just to the pure state 0, 0, or 0 outer product 0. Okay, so this is our simplest case of a model. This one's kind of a proto-agent, and the reason it's a proto-agent is that it only does one deliberation unitary, but it uses the output to choose between two different action unitaries that it might take. So it only does the poly X operation as its deliberation unitary, and for the case the poly X gets close to 0, it will implement the poly X. And for the case the poly X is closer to 1, it implements just identity. So that is, whatever the state was before I came along, I should just leave it the way it is. And that's gonna do better. So this is the control setup we have. And for those of you who know quantum information, this is just a C0 gate, but reversed. It's a bit flipped C0 gate. So this is what I said. If the control comes out to be 0, all right, yeah, if the control comes out to be 0, I'll implement X. If the control comes out to be 1, I'll implement I. And now we can just look at how this operation behaves. So there's one more detail here. So if all the environment states happen to be in the classical basis and the classical basis happens to be 0, 1, then this is a classical agent, or it implements all of our conditions perfectly. It satisfies our necessary conditions for agency, and it will be able to produce a perfect copy, or sorry, whether you give it 1 or 0 from the environment, it will succeed all the time to give you 0 back for the control state. Okay, so that's a special case. If you have a classical known basis, you can make clones and you can implement this kind of operation perfectly. But there's a limitation, even when you know the basis, and I'll show how the limitation comes in. That's for the case where I try to implement more possible deliberation unitaries. And so that really only applies to the case where I have a quantum environment where I don't strictly know what the basis is. But even if I have many copies that have been provided for me, so that was my second case. I can have many copies of psi, but I don't know for sure that they're in the 0, 1 basis. And that'll create a barrier as I try to add more and more deliberation unitaries. Okay, so this is the performance that you can see down here. So these are 2 of the cases. So the first case, it's classical. I succeed 100% of the time. Okay, that was my first possibility. For my second possibility, I'm given n copies. Okay, in this case, n is just 2. And so I look at the average over all 26 of those states that I could have fed into the circuit. And the average fidelity that I get is 2/3 for that case. The average length of the block vector, remember, is 1 for a pure state and 0 for a maximally mixed state is 0.733. And then I'm also tracking the angular error because the original state points in some direction on the block sphere, and I can look at how far away from that angle it is. So there are 2 different ways the fidelity can degrade for a state. One of them is that the angle goes off, it's pointing in the wrong direction, and the other is that the purity reduces and the vector's not as long as it was. So those are both independent things that can contribute to reducing this fidelity. But for this one, if we know already that if I give it the states 0 or 1, it succeeds perfectly. So there are particular states in the set here, that I'm using, the 26 states for which it succeeds. And then there are states for which it does very badly. And those are the states that are on the equator of the block sphere. The X and identity operation don't move you off the equator. So the state ends up staying there. All right, and now I can instead give this thing my entangled state of 2 clones. So this is, I've implemented the 1-2 cloning machine. I've got a symmetric entangled state of my 2 clones, and then I just act the same control unitary on them. I act a unitary of this form on them. And then I trace out the 2 deliberation qubits, and I'm left with some state of the target qubit. And you can see that, sort of interestingly, like the worst performance on fidelity is better. The best fidelity is worse. The average is the same. And there are certain areas in which this clone thing actually does better than the n copies. At least for the average cases, it kind of does the same. But then if you look at, let's see, is it this case? Sorry, I think we're going to see it in the next example. So yeah, the worst angular, okay, actually you can see one case of it here. So the worst angular error was pi/2 here, and the worst angular error is less than pi/2 here. So you can see there are certain ways in which using this entangled mess of copies to do your deliberation actually gives you some kind of an advantage. But again, this case is really not doing the thing that our classical agent was intended to be doing. It's not taking separate world models, deliberating on all of them. It's deliberating on an entangled state of all the world models. Okay, let's actually see how this works in detail for this particular case. So suppose I have an environment state, B plus A, and then if I act X on it, it gives me this here. And of course, these are normalized coefficients. So I act my circuit. There's my big unitary acting on just 2 copies. So this is, sorry, I should say, this is the case where we have 2 perfect copies that I'm walking through here, not the entangled case. Okay, so we have 2 perfect copies. Here's my deliberation. I act X on the first one. I act identity on the second one, so nothing happens to that one. Then I act my controlled unitary, and this is the control bit now. So for the A0, I implement X. So you see that here. I implement X on the second state. This is my target qubit over here. And for the B1, I implement identity. So again, nothing happens to the psi over here. And then this is the state that I actually get. And that's an entangled state of the deliberation qubits and the target qubits. Or sorry, there's only one of each. And And then in order to compare this result with our intended target, which was 0, 0, I have to trace out the deliberation qubit. And so here's the operation of doing that tracing out. And this is the result that I get. Just to make it fit, the first term is up on this line and then the other 3 terms are down here. And to see the fidelity, I just have to look at the coefficient on this 0, 0 term. So that's the fidelity that I'm getting. It's A on 4 plus B on 4. And you can see that if A or B is 1, this gives us fidelity of 1. But these are normalized, so A and B could both be 1 over root 2. That would be the states that are on the equator of the Bloch sphere, and then this is going to give us half. So this is how we're getting the numbers that you see. Yeah. Okay, so that's our simplest example case. Now let's move on to one that actually is what we consider to be an agent. So this is one that is very similar to the one I just went over, except that now it deliberates on 2 qubits. It does identity to one of them, and it does X to the other one. And it uses both qubits for its control. Okay. And because this one is actually doing a deliberation operation on 2 different world models, this is kind of the first one we consider to be like an agent. It actually tests out 2 different possibilities. The other one, sort of half an agent. It tests out one possibility and just says, I like that, I'll do that, or I wasn't so big on that, I'll just do something else that I know nothing about. So you can decide whether you want to call that an agent or not. Okay, so for this one, the basic idea is that if I've got my target or my deliberation qubits in the state 0, 1, then the control qubit should definitely interact or act I, right? This means I succeeded, got me 0, and X got me the orthogonal state. So if I get this for my output, I should act I. And if instead I get 1, 0 for my output, that means X succeeded and I failed, and I should act X instead. And now for the 0, 0, and 1, 1 case, neither is better or worse. And so this is a case where we'll implement a superposition of the 2 deliberation unitaries, because there's really no reason to favor one or the other. And so we can get we think we can get a better result by implementing a superposition of them. And by making this coefficient I, I'm able to make it so that this sum of 2 unitaries is also a unitary. There are a bunch of special conditions you need to satisfy for that to happen, but this is one case where it works. And I mentioned earlier that there's some freedom in how I construct the CU. And I'm gonna construct I'm gonna go through 4 sort of examples to give you a sense of what's going on, but there's like an infinite number of these that I could make. And even the sign of these I's here is actually arbitrary. I chose to make a superposition. I could have just put whichever one I want. As long as the mod square of the coefficients are the same, then these are equally weighted implementations of I and X. I've chosen the signs that are here just because it resulted in an agent that worked a little bit better. And so I just tested a few cases and chose this one as our example. Okay. So this is then the action we're going to get for our agent. I've just gone over this. We'll implement I, X, or superpositions of them. And there's no particular reason that that's the positive one, that's the negative one, but the coefficients, it's arbitrary. Okay, and now we can take this circuit and act it. We needed 3 qubits this time, so that meant that we had 3 qubits, 3 perfect copies in the environment, or we knew we had a classical basis and we could make 3 perfect copies of it. We knew we had state 0 or 1, or we're going to consider a case where we've created a symmetric entangled state of 3 clones, and we'll use 2 of them for deliberation, and 1 will be the one we act our unitary on. Okay, so in this case, wrong button. So in this case, you can see how we're doing. This one, if you actually look at these numbers, for the n copies case, it's identical to the previous one. That wasn't something I expected. It's interesting that for the pure copies case, the one where you only open, you only check one and then decide whether you're going to do that one or some other one you know nothing about, it gives the same exact result as, on average anyway, as doing this one where you have 2 control qubits. But because I had to make more clones for the second case, some of these numbers are worse. The fidelities are about the same, but there's some degradation that happens in these. The clone case kind of seems to like move the best case towards the average and the worst case towards the average. So in general, the worst cases get a little bit better, the best cases get a little bit worse. Yeah, it still works reasonably well. But I guess I should say, by reasonably well, the average fidelity we got in both cases was 2/3. That's really not that good. With 2/3 of success probability, we got our thing into the target state. And it's clear we didn't really do it by implementing just one of the unitaries. We implemented some mixture of it. So we have something that's not really acting at all like our agent, but it is doing a kind of, stimulus response thing where it does take in some inputs from the environment, and it does do something to the environment, which does get it kind of close to the intended state, but really not that close. And, well, we can talk about how successful an agent is if it, is not our deliberative kind of agent, where it deliberates on separate cases, picks the one it likes best, does the one it likes best. This is something much messier than that, but still it's, able to do something to move the environment in a way it likes. So this is not going to be the kind of agent we're talking about, but there might be some other notion of agency, quantum agency, that maybe could be applied to these kinds of things. Okay, now let's look at a more complicated case. Now I'm going to add a third deliberation in. This one's going to be a Hadamard. And so now instead of having only identity and X, which just is a bit flip, X just brings you from a point on the south pole of the southern hemisphere of the block sphere to the north, or the other way around. The Hadamard is sort of partway in between. It can do like a 90-degree rotation on the block sphere. And so this is going to now allow us to rescue states that are on the equator. But there's a cost. Having a third deliberation unitary in here ends up meaning that it's now impossible to avoid getting a mixed state. So I won't be able, I guess I'll come to this point in a second, but I won't be able to have this work perfectly for a classical basis anymore. So again, it is possible to superpose the Hadamard X and identity and have them be unitary. The coefficients you need to use are very specific. And again, the signs here are somewhat arbitrary. They're not entirely arbitrary because this plus goes with a plus in this coefficient. You can see here I've got the minus version of it. And I could have chosen those arbitrarily, and I would have had to change the coefficients in a corresponding way. But there are ways to make superpositions of unitary that come out. So now we have 3 control qubits. So if I get a single 0, so a case like this, I know that I should implement only the second of my unitaries, the Hadamard. And if I get this case, only the third one succeeded, I should implement X. And if I get this one here, I should implement I. But then there are some where I have 2 zeros, and so I'll implement a superposition of those 2 unitaries. And there are some where I have either 3 zeros or all 3 are 1s, and then I'll implement a superposition of all 3 unitaries, again equally weighted for each of these cases. And the way that I chose the signs and the corresponding coefficients was again arbitrary. I just chose values that made this one work reasonably well, or as well as it could. Okay, so now let's look at how this one performs. So you can see that I actually am doing something interesting here. The fidelity, the average fidelity, which is the same for the 2 cases, the clones and the other case, the clones and the copies, is better than 2/3. So by implementing this funny circuit, I actually can get the fidelity to be a little bit better than my very simple cases. But there's a cost, and you can see it in the block length, right? There's more degradation in the purity of the state. It's closer to the mixed state than the other ones were. So, and the angular errors are still pretty large for this. So for this particular one, I can get a fidelity that's, close to 0.7. And maybe there are other ways to design these circuits where you can get even better. But as you start to have more and more of these controlled unitaries these deliberation unitaries that you're using, and more qubits that you're using for them, it's inevitable that they're not all going to map exactly to a state that's just a single 0 and set of 1s. So it's not going to map to a state like this or like this. And what that means is that no matter what, I will end up implementing something that gives me a mixed state where I've implemented some of these different unitaries in a way that sort of overlaps. And then when I trace out the deliberation qubits, the purity of the thing I'm left with is reduced. So one of the trade-offs in building these CUs is that the more deliberations I want to use, the worse the purity is going to get in general. And so maybe I can improve the state in other ways. Kind of depends on what's important to me. But I'm not going to be able to implement a huge arbitrary number of unitaries and have that help me to get a better state in this way. There's a diminishing returns as I add more and more unitaries in. And now let's look at one final case here. So this one has 5 qubits. I'm actually going to implement all 3 of the poly operators, but because my target state is 0, I want poly operators that don't have this as an eigenstate. So what I'll do is I'll rotate all of the poly operators in a particular way so that they all have expectation value 1/√3. So a way to visualize this is if I have my x, y, z coordinates, there's a vector that points symmetrically right in the middle. And I'm just making that the North Pole and making my x, y, z point sort of unbiased around it. Okay. the reason I chose this particular construction is that now each of the x, y, and z has a chance to improve the state in a different way. And so we're going to see how well this will allow us to improve the state towards the state we want. So if I had kept the original x, y, z, the z wouldn't really have been able to do anything for me at all, and the x and y would have been the same. So this allows each of them to do some independent thing which could benefit improving the state towards the target state. Okay, we have 4 control qubits now, so this is getting increasingly ugly, and you can start to see why we're going to end up with all these mixed superpositions. So again, if I have just a single 0, I'll implement the corresponding operation. If I have 2 zeros, I'll implement the superposition of those 2. If I have 3 of them, and so on. Okay. So this is what I have to do now. This is my controlled unitary operation for my 4 deliberations up here. And I can act this on my target states. Sorry, I can act this on either of these 2 cases. So just like the previous one, this one will not work for the classical basis, because the only way the classical case works out is if all of my deliberation unitaries lead me to a single state as the correct state. I can always choose my unitaries if I know the basis and construct it that way, but only if the number of unitaries matches the dimension. If the number of unitaries exceeds the dimension, then it's going to be impossible to avoid a case where I end up with a mixed state that's more entangled and has more loss of purity. So this one is interesting though. The fidelity is worse. It's a little bit worse than 2/3 on average. Notice again that it's the same for the copies as it is for the clones, which is interesting. And again, that the worst cases got better, the best cases got worse. But a thing to notice about this one is that even though the fidelity got worse, the angular errors got much, much smaller. So now by having this sort of symmetrically spread out set of unitaries that I can use, I have sort of more possibilities to get the state pointing in the right direction, which is in this case, the goal is to get pointing in the North Pole. But I have this purity lost because I'm using more deliberation unitaries. And so the fidelity goes down, but I can get better matching of the angle. But again, notice that the block lengths of these things have gotten really small. If that's 0, that's the maximally mixed state. And so you can see the cost of adding more unitaries in. I'm starting to see the block length here is the one which kind of tells you about the purity of the state. So again, these are both sort of independent things that can cause the fidelity to go down. And so the previous case, we had better block lengths, better fidelities, but the angular errors were worse. In this case, we have worse fidelities, better angular errors, and that kind of happened by adding in another unitary, another deliberation. So it is possible that someone will construct a better CU than any of the ones I've got here, and that it will somehow, do a better job of getting high fidelity and maybe better angular error. But I think these 4 examples give a sense of kind of what the space of these possibilities is like. And there's really nothing, as far as I can tell, there's no like particular path you can follow that just makes everything work out great. There's always some cost you have. You try to make one part better, something else gets worse. And so it seems like there's not really any way we can construct this kind of a quantum agency circuit that's going to do very well as an agent. The only way that it works out reliably is for the cases that only have a small number of unitaries and they are tied in a corresponding way to a known basis. And that's our classical limit case. That's the case where you can succeed every time, you can satisfy all the conditions of agency. I know I'm calling this a classical limit. I don't mean H bar goes to 0. I just mean that we're able to recover our notions of agency. So this is maybe a somewhat new and alien notion of what a classical limit is. Though one of the notions of classical limit that's out there in quantum mechanics is that there is a preferred basis. So it sort of matches up with that one. Okay, so this is it. Just going to go over our sort of main discussion points. So we've argued that agency always requires copying and comparison of world models, that a purely quantum agent really can't do this. No cloning blocks them from making copies of world models. It blocks them from getting copies of the environment state. There's even some other sort of more subtle ways in which no cloning interferes with your ability to be an agent. In particular, if you have to deliberate about possible states of the future, if in like the case of the walking to school, it might rain or not. You might have to consider multiple world models for a scenario where it rained and a scenario where it didn't. So you might end up needing even more clones for that. We haven't really formalized how that would look, but in general, there are a bunch of places where you sort of need to be able to look back at the same information to do things. And classically, we do this all the time. We just keep a record of some important piece of information, and I can email it to all my friends, and I can look back at it as many times as I want and use it for things. And that's just not how information in a quantum scenario works. If you don't have collapse, again, there's no measurements in any of this. You're stuck with purely unitary operations. Okay, so our final conclusion is that agency cannot be purely quantum, at least not the deliberative kind of agency we're talking about here. And as we've talked about, there are some other notions of agency. Maybe someone will come up with some abstract notion of quantum agency, but the specific kind of deliberative agency we're considering here, which really corresponds to the kind of deliberative agency that we experience. That's the part that we really can't implement in the quantum computer. And yeah, the agency seems to emerge in the classical limit. So even if in some of the cases I did hear, I still implemented this quantum circuit. Everything was done in a coherent way. It was just by knowing the basis that allowed me to get all the effects of the classical agent. So again, there is sort of a classical limit here, but I didn't do anything to make the operations classical. I just had the constrained basis, and that was enough to do the job. All right, and yeah, we think that this result might place some interesting constraints on theories of free will, theories of consciousness, theories of quantum AI, a lot of different things people are starting to think about. All right, that's all. Thank you.
Earlier point about uncomputation, because it seems to me that standard approaches in quantum computation are a counterexample to what you just said.
Don't those always end in a measurement and collapse?
No. So if you look up in a quantum computing textbook, the concept of a quantum subroutine, I think this is what you're trying to do. So if you think about one of your deliberations of the agent on different trial realities, think of this as a subroutine that you're trying to implement. The way this is done typically is that you have a register internally that you initialize to all zeros. So me as an agent or the computer as an agent knows the initial state of two registers, one of which will be the output register, the other will be the memory of the output register. Then you have an arbitrary number of kind of computation bits. This would be your environmental data or whatever state psi that you don't want to copy because you can't copy it, right? So what you do is you run a computation unitary that takes your output bits, all initialized to 0, takes your input psi, runs some computation on this. And you can arrange the computation because you know the input is all 0 on your register. You can arrange the output of that unitary to a product state. So then you have a product state of your results in your register, of definite bit values in your register, and then some other state psi prime of your other bits. Now what you do is you do a controlled knot between your output bits to your memory. And because they're definite bit states, they perfectly copy all of them. They're product state, they're not entangled with your psi prime. So you store a copy of your output in your memory bits.
Okay, but that controlled knot does entangle all of those qubits together.
No, because it's a product state.
Right, but when
And
you
a controlled knot, because these are definite bit states of 0 or 1.
Oh, I'm sorry. Okay, I see what you mean. Yeah. Okay, so those are just 0 or 1. Yeah.
So I get a perfect classical copy because these are just classical bits. Now what I do after I've copied those to my register, my memory, is I undo my computation, you inverse on my output bits and psi prime. And after undoing that computation with the inverse computation, I have now restored my state to 0, 0, 0, 0 and the original psi. Now I can redo this with a different memory copy, with a different computation, U prime, U1, U2, whatever. So I can just keep reusing the same.
So you never clone it, you just keep reusing the same copy.
You never clone psi because you can't clone it, but I can use it as a resource over and over and over again by doing a computation, copying the output, undoing the computation. So I just repeat this. This is known as a quantum subroutine. And it's a standard part of many of the most successful quantum algorithms. What I'm not yet understanding is why that's not a counterexample of what you're saying. Just to remind you that that is how it.
Yeah, no.
I mean, that can't work in general for what we're doing, because if you could do arbitrary calculations that way, you could just do tomography on your unknown state, and you could find out the exact state of that method.
Well, in this case, there's no measurements because you arrange for the unitary output to leave you in a product state of definite bit states in your output register that you then copy. So I didn't have to do any measurements.
I mean, what we're interested in doing is taking the input state and performing various unitaries on it and seeing what the resulting state is. And if we could just do that and then undo it and do it again many times over, then we could just do tomography.
Well, I'm not interested in knowing what psi is. I'm interested in deciding something based on what psi was. So the decision process is in my output register bits.
Yeah, but if you know psi, you can do anything you want.
If you could do that accurately, but by just repeating like that, you can just figure out what psi was.
So as an example, like suppose I'm at a stoplight as an agent and I want to decide should I hit the accelerator or not. and I'm using as my input of my environment, like light is green or red or whatever. I don't need to like do tomography on the entire environment. All I need to know is the single bit, yes, I hit the accelerator or no. So what I'm doing is I'm evaluating as a like decision-making process, the computation, using all this info in the environment, whether or not my output bit is a 0 or 1. Then I can undo all of that, forget all about my environment. And as long as I retain whether or not I hit the accelerator.
Binary result. What each of these things implements is we take a state, we perform some operation to it, and then we want to see how close is it to 0. And if you could do that arbitrarily many times, then you could just check every single unitary and you would know exactly what state you have.
And there
It
must
might
be,
be possible that you could check for every possible unitary on the sphere how close the result is to 0. That
Seems like moving the goalpost slightly. So I agree if you're trying to do some arbitrary thing. Yes, that would be possible, but usually like an agent is reasoning about something very specific.
right. And in this case, our agent is reasoning about how do I turn this unknown state into 0.
Yeah, so the choice of what algorithm you perform has to be specific, and there has to be some knowledge in the algorithm of things that I'm looking for in that environmental state psi. I don't think you're trying to determine the entirety of psi.
But what I'm saying is that if what you're saying is possible, then I could determine the entirety of psi. Because I could just, if I could test as many unitaries as I wanted by that, if I could for sure figure out what psi was. There must be some limitation in what you're saying on how many unitaries I can assess how close it gets me to 0.
So I think the limitation is that what I just described is getting classical bits as output.
Yeah.
But psi has sort of an infinite number of bits in terms of its precision of amplitudes, right?
Exactly.
So I'd actually need an infinite number of register output bits to even get an approximation of the total content of psi. That way, if I had an infinite amount of memory and I could run it an infinite amount of times, then probably yes.
That would violate that cloning theorem still.
yeah, that's what I was asking. Yeah, something, you could just take all those memory output registers you were talking about and run them backwards and you would.
But I'm not cloning it. I'm getting like a binary approximation of all
The
this.
subroutine thing will only bring you back to the original state if have a subroutine that has definite bit string is now.
Yes, but only for certain computations. But what I'm saying is that this is a counterexample to what you're saying.
Well, not really, just lots of special cases.
So we said the setup was that unknown state, you have no expectation that your unitaries are going to be aligned with it any specific way.
So what I'm saying though is this is an example of there exists an agent operating purely unitary that can make some decisions about certain questions.
Oh, yeah,
It
sure.
doesn't violate anything.
Like we set up conditions quite specifically that the agent has to do a certain kind of procedure. For sure, like quantum agents, as Kai said, can achieve something. You can get it closer to 0 in some cases. But you can't do the specific thing we asked.
And also the classical basis case I showed does what you just said. It does succeed. So there are cases, there are particular cases where it works. It's just that it won't work in general.
An agent doesn't really know about arbitrary things either.
Well, again, an agent who's, having to respond to something completely new and unknown in their environment, that's the thing they have to reason about. And if you assume they have no a priori knowledge about what that state's going to be, then in general, none of these protocols will succeed every time.
Yeah, I'm wondering if you're demanding too much quantum agent compared to the classical agent.
Maybe.
Classical agent is precisely that it has a third basis. Which
I tried to
that's
answer.
what where the point of our results is that we don't have a third basis. We can't achieve the same thing.
Okay, there are too much people who want to speak, so I decided to take the control of the situation.
Marco, you're in a
I
zero.
want to take a slightly different tack. Because the task that you've chosen to analyze is quite interesting, because it's one that we at least try to do all the time, right? So you want to do a quantum computation, you have to reset whatever register you have into the all 0 state, so you know what it is from whatever it happens to be. But of course, we know some ways of doing this, right? So for example, suppose your 0 state is the ground state of some Hamiltonian. And what you would do typically is like slowly cool the system down as low temperature as possible.
Right, that would be non-unitary though. So that's why we're leaving it out. Yeah.
It's non-unitary if I just consider the qubits I'm trying to prepare and my own internal state. But if it's that and thermal environment it's in, then that whole thing is unitary. So why is this not an example of so it doesn't matter what the initial state of the system is if I do this sufficiently slowly, and if I do it then I'll always go back to zero. And then I can also deliberate. I can say, well, suppose I have one procedure which takes me down to a temperature T1, and I have another procedure that takes me down to a temperature T2, and T2 is lower than T1, then I'll find that T2 is better at preparing the ground state.
I mean, I noticed that the task we set wasn't just about reset everything to zero. The task we set was specifically meant to be about comparing different possible actions.
So that's why I'm saying, like, have two different temperatures, right? Both fairly close to absolute zero, but one slightly higher than the other.
But I mean, it's not just supposed to be, comparing in the abstract two possibilities. It's supposed to be taking information from the environment, assess the consequence of different possible actions, conditioned on what we learned about the environment, and then.
But the point here is that neither of those procedures really depend. So if by the environment you mean the initial state of the thing that you're trying to reset to zero, neither of these procedures depend on what that state is.
Well, exactly, but that's why we're interested in this task, which involves comparing actions based on what the external world.
Yeah, but the thing is that you don't need to know the external world. What the state of the external world is in this case.
Right, but that's not the kind of procedure we're interested in what we call agency.
And we're looking for like stimulus response. You get something from the environment, that you observe or sense in the.
But what I'm saying is that in order to achieve the task that you want to achieve, there are optimal ways of doing it, which don't require you to know anything about it.
I mean, that's true for many non-agential systems. Like I wouldn't call a thermostat an agent in this interesting sense. Thermostats can achieve the task you want them to achieve.
Listen, if you're going to say that there's limitations to agency, then you have to choose a task where in order to achieve that task, you need the information from the outside world. If you choose the task that you're going to compare and model to be one which has an optimal way of doing it, which doesn't require information about it, everything you're doing with the modeling is unnecessary. You're going to achieve an optimal result without any of that.
I'm not sure there is really any such time, because if you give your agent unlimited possibilities to sort of reset the environment to any state they like, then of course they're never going to have to consult what the environment is like.
Can we also ask questions over Zoom?
Yes, you can take, yes. By the way, it would be good whether I could see people on Zoom. So, go, Uri. Go, Uri.
Okay, I'll turn my video on if you want to try to see me. Hi, can you go back? I think it was slide 2 or 3 where you defined the agents.
How the money you have. Feel this one.
This is probably going to take a bit of time. Sorry. All right. Okay. I have a problem with a few of these, but let's concentrate on number 3. Perform the action which leads to the highest expected utility. I mean, and you gave some examples from the 50s. Of course, after that, we had Kahneman and Tversky and other things that suggest that, I mean, none of us would then be agents according to this definition. And more than that, it seems that you're really using that number 3 later on in your assumption. So you need to justify that, I think.
Yeah, so can you say why we would not satisfy that condition? Because again, when we're talking about the highest expected utility, it's like a subjective thing. It's what's the best outcome from my particular subjective perspective. And then the idea is once I've figured that out, I'd take that action.
I think the point is that most agents aren't rational.
Yeah, but
I don't think you need to necessarily be rational to be an agent. You're making some rationality assumptions, and even I don't know. I'm not sure exactly what it means to be subjectively rational here, but
so what I meant by that was if there's some sort of objective criteria for what the best action would be, that's not what we're talking about. It's just from the subject's own perspective, what is the most desirable outcome. We want them to be able to perform the action that gives the most desirable outcome. And maybe you can't do that every time, but presumably you'll agree we can do that at least sometimes.
If it's an extremely simple situation, you can really do these computations, perhaps. But if you really need this assumption, then I think that most agents, most of the time, do not do what they think is optimal, but rather good enough. But anyway, I don't want to belabor this point with a lot of other questions. I just
in philosophy of mathematics, there is a position that is called if-thenism. So it seems to me that you have an if-tenist situation. And what you have proved that if the agent is this, then is a quantum system cannot be an agent.
Well, but that goes back to like, would it be an interesting notion then? Because to Uri's point,
Exactly.
we want this to be relevant to human beings.
And the study is this: if an agent is there, then.
Another point to make here is that, like, one of the major reasons we have condition 3 is that you have to pick one action. It's not necessarily about being the one that has the best utility, whether that's subjective or objective. It's just that you have to pick one. And what the proof that Emily went through is to show that the agent in general cannot choose just one action. But in our experience, whether we choose an action we like or not, or we have reasons to, and this is the one I would prefer, but there are other reasons that are making me not choose that one, all of that goes into the utility calculation. And then you pick the one action that is the best utility with all of those things taken into consideration. So it doesn't have to be a rational agent at all. It can make a terrible decision that it thinks has high utility.
It's also worth noting our assumption is not that agents always do perfectly this every single time they take any action. The assumption was that agents should have the capability of doing approximately, should be able to at least approximately compare different alternatives and see which one hits the outcome they like the most and then form that. I think it's clearly the case that we do sometimes do that. For sure, not all the time, but we do sometimes do something a lot like this.
Please.
I just wanted to ask if quantum computers are Turing complete, and it's like, then if you can run a agent on a classical Turing machine, why?
You need collapse to get Turing completeness for a quantum computer.
No.
No, you don't.
No?
No, but you can get Turing completeness just with a fixed basis, right? So.
Oh, okay, yeah.
That's fine.
Yeah, you know exactly what that says.
It's
It's a
only
strict superset of classical computer. You can do unitarily every classical computer.
As long as you're in the numbers.
Yeah, because you're starting at a definite state of bits, then you get a unitary computation. So you get no drawback at all over.
You can measure in that basis
Every
frequently.
possible on a normal computer. It's just if you do superpositions and allow for other bases and so forth, you can also do that. But if you're doing strictly classical computation, you can do it unitarily.
So that's what we're asking that this agent to do is not something that a classical computer could do because there's no such thing as unknown quantity state has been input to a classical computer.
So this means that a classical agent you can simulate on a classical computer can be done unitarily on a quantum.
Other questions? Okay, so can I ask one question myself? So I'm manifesting some doubt by the fact that is a fightful description of what an agent is. Agent is what usually we understand as agent. But I think that there is a point important here that even if an agent does not always behave in this way, certainly it should be someone that can behave in this way. I'm sure that they do not behave always in this way. I'm sure that there are a lot of agents that do not behave always in this way, but someone is not able to behave in this way, probably is not an agent. So I think that this seems to me a point in your favor. But now, if I'm not able to evaluate technically whether your answer is correct or not, so I suppose that you convinced. You did not convince me, but not because you did not convince me, because I do not know enough the technicity that you're using in order to appreciate your argument. But now I want to understand the impact of what conclusion. So I suppose that you agree that Kelvin is an agent insofar as able to work in this way. And I suppose that you agree that Kelvin is an agent that is able to work in this way because as a brain they work in a certain way. It's not because I have an arm or legs that is an agent, but because it's a brain. So does your conclusion is that his brain cannot be modelized as a quantum system?
Not a purely coherent quantum system, I would say.
Sorry?
Not a purely coherent quantum system. But it's possible that Kelvin's brain exists in an Everettian scenario where everything is really quantum, but there's some decoherence regime in which things act classical. So that's fine. That's not opposed by our results. What is opposed by our results would be the idea that Kelvin's brain is a purely quantum agent acting in a coherent regime without decoherence or collapse.
Maybe a thing to say is that we think that a much more plausible model of a quantum agent would be a hybrid one that is, and that's much more like what's happening in most quantum information processing.
Okay, so your point would be that we cannot modelize its brain only as this one, but we could imagine that at least some aspect can be captured by a quantum system and some other aspect no.
Because agency is this kind of modeling process is a very important part of what our brains do, and to us, definitely the results indicate that there are quite strong limitations on to what extent important things in the brain could be purely coherent.
Okay, but now another question. It seems to me that you reason under the opposition quantum classic. So even it's not quantum, it's classic. And what does it mean classic? Mean Newton mechanics or something like that? Is there a third possibility?
In our context, classical most.
What does it mean classic? This is the question. Does classic mean non-quantum? It seems to me.
In our particular classical mostly means there's a preferred basis, which is in a particular context, classical mostly means there's a preferred basis which the agent knows about and can take advantage of. So that's a specific notion of classicality that's relevant to this kind of task, and that is certainly part of the classical world that we live in. And I would say that's sort of mutually exclusive, either there is or there isn't a preferred basis. There might be other things that are not very classical in the sort of ordinary sense, which perhaps fall into the preferred basis realm as well.
So to a non-physicist, this sounds extremely technical. So what does preferred basis has to do with classical?
It sort of means that you can just get away with using classical probability and everything, like just assuming that you don't know what the state is and you can just use classical probability.
Okay.
So it's more like the limit of quantum probability going to classical probability.
Under this respect, I want to make a remark. After I want to make a remark from history of science. After the extraordinary success of quantum physics, there was a lot of discussion overall in France, but not only in France, about the fact of whether Newton model could be a model for anything, that we could use it to describe anything. So there were a lot of tentatives to apply Newton model to biology, to behavior, etc. But then something happened. And something happened, a lot of things happened, but one thing that seemed to be very relevant that happened was Fourier of it, that made clear that there are physical phenomena that is not good to study. The Newton system is not the Newton pattern, let's say, to say it this way, is not apparently not the good one to study this phenomenon. So
do you mean by that statistical mechanics as opposed
to simply, and then there was all the mechanical continuum system. So I want to say Newton system was a particle system. Okay, then is deterministic or not deterministic, think as you want. But the fundamental point is the phenomenon you study is made by n particles that interact one with the other. And the real model for the diffusion of it was not made in this way. But there are then a lot of other systems appear. For example, the continuum, the elastic body, in some sense, is also not Newtonian in this sense, etc. So all that is classic in some sense. It's not quantic, but it's classic, but it's absolutely not the same thing. And so I am a little bit afraid that we are in some sense in the same situation. Insofar quantum mechanics is very good, it's very successful. So we wanted to use quantum mechanics to play anything. The answer that we can is very doubtful. The answer that we cannot is possibly correct, but it's not so much explicative. So that's what I want to say. When you say, okay, this is not a quantum system, okay. What does it explain that now we have a good model, a good system to explain how the brain works? So I don't know. That seems to me, I don't know. It's not a criticism. It's a reflection. It seems to me that you are in a similar situation that the discussion in France in that of 18th century, when people wanted to apply Newton pattern everywhere, and then.
So is this part of what you're saying, that we've shown that the purely quantum system is not possible, and then we just jump to say, well, it must be classical, but then maybe there's some.
No, yes, you jump and must be classical, but the problem it must be classical. I do not understand I do not understand. It's not that I do not understand. It seems to me a very vague notion.
Maybe one thing is just when we have these purely quantum systems and we're showing that they can't be agents, and then we show what we need to add to them in order to make them agents, like giving them a preferred basis in the environment,
exactly.
Sort of it's showing what's needed.
Possibly would be much exactly. Your analysis could be enriched in this way. Okay, quantum system cannot do that for that, and that. So what we have to add in order to make it possible to do it? So then at this moment, the question is simply not negative. Now you are doing something more.
Can I ask something? Because I am picking up what something that Matt said before with a preferred basis giving you classical probability theory, but you start from Savage kind of utility theory. So you start from probability theory, and then you make a big detour and say, oh, I need to make quantum theory so that it agrees with probability theory, but you're just going in a circle, maybe.
Didn't really appeal to probabilities because we assume that the actions are more deterministic in this case. So in this particular case, you don't actually have to worry about anything.
So there's nothing about expectations and probability in your setup.
No, because we just imagine the agent comparing various different unitary operations. Each of them produce a deterministic result. So we don't actually have to calculate any expected values. But each operation just produces one different outcome.
We don't have to think about, does it rain or not if I walk? It's just I walk and everything works out in some deterministic way.
Okay.
Yeah.
Go.
So I want to make like a technical suggestion for something to look at. So in quantum biology, there is this model of the avian compass, which may not be the correct way of how this works, but it's a model of how the avian compass works using entanglements and splits. Their coherence is relevant to presumably the decisions that the bird makes about which direction to fly. So that is a sort of very concrete model where there's a decision-making scenario based on some piece of quantum information that's presumably, inside the bird's brain. So the question is, does your result rule out this kind of model, or does it, or how is it compatible with?
This would be an example of a hybrid quantum classical system. So, like, we look at an actual quantum computer, depending, or maybe more generally, quantum information processing hardware. There are lots of scenarios like error correction, where I measure some of the qubits, use the output to do some unitary back on the ones that remain coherent, or to reentangle more, and then I just continue the computation. So there are steps where you do some classical measurement of your coherent quantum thing, and that's the part where you would be able to do some classical agency. So if you add measurements in, even if you don't fully collapse your state, then you get like a hybrid, some kind of hybrid scenario.
Other remarks? Okay, so I think that we can close.